Hello, Physical Science 20. Welcome back to Physical Science 20. We're going to have an abridged version of the rest of this course while you guys are at home during this pandemic. We're going to try to learn a few of the basics that we're currently missing, but we'll try this format where I record my lessons just by voice. I'm not going to put my little face in the bottom corner of the screen anywhere. It's just going to be my voice, and we'll see how this goes. So I have my schedule up for the rest of the semester online. We're going to skip quite a bit of it. For instance, last time we were together, we were talking about heat and chemical reactions. So that was March 13th, just after thermodynamics, March 12th. We were going to spill into Hess's law, but Hess's law is just a slightly different way of doing the exact same thing of heat and chemical reactions. So we're going to skip that. The notes are online if you want to read about it. I'm not going to test you on it. And for the rest of this unit, we're going to basically look at specific heat capacity. We're going to do thermal equilibrium, and then we're going to talk about latent heat, which is state changes, but we're going to skip over the math for thermal expansion, and that'll sum up the rest of this heat unit. Obviously, we're not going to do the lab, but that's what the rest of this unit's going to look like. So what I'm doing is I've made a few changes for the notes that are online. If you want to read all the notes that are online, they're still there. Practice problems are visible still. If I open them up, it'll show you basically what I would have handed out to you in class. Nothing has changed there. Scroll down, there were 7 questions that you should be able to do by the end of today's lesson for specific heat capacity. My next lesson, I'll focus more on how to do these ones, mixtures. It's thermal equilibrium. It's a little bit more complicated. But yeah, that's what we're going to do today. So if I get to the lesson, so specific heat capacity is referring to the heat holding ability of any substance. You might notice that most cookware is made out of metal. So your frying pans, your cookie sheets, most of the time it's made of metal. Sometimes you will use glass, sometimes there's ceramic pans, but most cooking utensils are made of metal because metal has a really low specific heat capacity for the most part. They do not hold on to heat very well, so that means they heat up fast and they cool off fast. They do not hold on to heat well. Unlike things like water, water has a very high specific heat capacity, which means it takes a lot of energy before the temperature of the water is going to change for any given mass of water, which is why if you are going to make ramen noodles or Kraft dinner, macaroni and cheese, you have to boil water, and it doesn't just instantly boil. You have to put it on the stove, put it on high, and it takes a good 3 to 5 minutes depending on the mass of water you're using. But the pot got hot really fast. Likewise, when you shut the element off, if all you had is boiling water afterwards, if you put it off to the side, 5 minutes later, that water will still scald your hand. But if you dump the water down the sink and then just put the pot off to the side for a minute, you should be able to touch the pot with your hand again, because metals typically have low specific heat capacities. They have very low heat holding abilities. So today, we're going to talk about specific heat capacity. That's this equation right here. So delta Q means the change in the quantity of heat energy. So we measure our heat energy in something called joules. And the unit for joules is just a J. Writing with the mouse is terrible, but there it is. Capital J, not lowercase j. That's what we use for the symbol for energy. Can't see the pointer. There we go. Mass, of course, in physics, we tend to use kilograms for mass. If we were sticking more with chemistry style, we'd use grams, but we're going to go with physics on this and use the kilograms. So that's just 1,000 grams. The specific heat capacity, that is, well, specific, particular to every single substance. Every single substance has its own specific heat capacity. So waters would be 4,200 approximately joules for every kilogram degrees Celsius. Something like aluminum, I believe, is somewhere around 900. So you can hear already that it's a lot lower than that of water. So this is going to be very material specific. You just have to pay attention to the questions, what's being asked, what givens you have to determine what your specific heat capacity is. So the units are a little bit ugly to look at. So if I write it out sideways, it's a joule / kilogram times a degree Celsius. So if I write it off to the side here, that means for every amount of mass to go up by 1 degree Celsius, we require a certain amount of energy. And so if I write it as a fraction, the joule, the amount of energy is on top, the kilogram, the degrees Celsius are down below. I can't see, there we go. I'll just get rid of this shade. So I've got it written off to the side here as well, joule per kilogram Kelvin. And that's because we're talking about a change in temperature. So delta T just means change in temperature. And if you remember one of the last few times we were together, I might have said something along the lines, we were talking about Kelvin at some point. Kelvin and Celsius use the same scale, they just changed where 0 was. So that means if the temperature goes up by 1 degree Celsius, it will also go up by 1 Kelvin. So their delta, their change in temperatures are actually the same. I'm not saying 1 degree Celsius is the same as 1 Kelvin, but their change is the same. So that's why you can interchange the degree Celsius with the Kelvin in this scenario. But that shouldn't be something you have to work with too often. If you want to read a textbook, I have a textbook page, a little chapter of a textbook linked online as well. So you can read these 6 pages if you want some more detailed information. So that's really all there is to it, specific heat capacity. So that's the equation. In that print off, if you printed it off or just left it online, you will see a quick chart. Now this is a simplified chart. It's only showing 2 significant figures. For instance, water I know should be somewhere around 4.186 more approximately times 10 to the 3, or 4,186 joules per kilogram degrees Celsius. This is just a simplified version for what you guys need. The simplified version is good enough. But you can take a look down this list. You'll see that most of these numbers for the 2 alcohols that are on here, aluminum, brass, copper, the 2 types of glass, they're all in the 100s for how much energy is needed for every kilogram of substance just to go up by 1 degree Celsius. So that's again what these units mean. How much energy is needed. So if I had copper, for instance, I would need 390 joules of energy just to change the temperature of 1 degree Celsius for every kilogram of substance that I have. So that's where the math equation comes in. If you don't have a kilogram, you need that equation to find out what the equivalent is. If you want to change the temperature by 10 degrees or 4.6 degrees, again, that's where the equation comes in. So for most of your guys' cookware, you'd probably have some kind of steel pan. So the main ingredient of steel is iron. So iron is somewhere around 450 joules per kilogram degrees Celsius. And as you get older and you start buying your own cookware, you'll see that sometimes companies who make pots and pans will usually graft copper on the bottom of their pots and pans, and that's mainly because copper has a lower specific heat capacity, which just basically means it heats up quicker, it cools off quicker. So that might be why they'd use copper on the bottom of some of those pans. Some people have glassware for their cookware. Glass takes longer to heat up, but glass is also transparent. So it would allow a lot more infrared radiation to go through. But so sometimes people like to use glassware for cooking things. So you can look at this list if you want. Water is on this chart in 3 states. So water is the highest value on this chart. So again, around 4,200 joules per kilogram degrees Celsius. In its solid form, it's about half the amount of energy to change the temperature by 1 degree. And in its vapor form, so steam, so gaseous form, is also about half of what it is when it's in liquid form. So liquid water requires a large amount of heat energy just to change the temperature. And that's mainly why coastal regions like out in Vancouver, for instance, or Victoria, or on the East Coast in Newfoundland, most of those coastal regions are very temperate because there's a lot of water around there. In the middle of summer, the ocean's still pretty cold because it had the winter. It's still suffering from the winter. It's takes a lot longer for that water to heat up. So it's not until about August or so when the waters start getting a lot more agreeable. And likewise, come wintertime, the water is holding on to that heat energy from the summer. And that's why it has that effect come wintertime. That Vancouver is rarely ever ridiculously cold like it is in the prairies where we have no water. So there's nothing holding on to the heat over in our region. So that's a chart that you'll need to reference when you guys are doing your homework. I'll do 2 quick questions to kind of give you an idea how to do this stuff. So for instance, how much energy is required to heat 2 kilograms of copper from 30 degrees Celsius to 80 degrees Celsius? So when you read a question like this, first thing you need to do is figure out, well, what is it that we need? So you want energy. So energy is delta Q. That's your change in the quantity of heat energy. Try to highlight what's given to you in the question. So I see I was given 2 kilograms. So right away, I'll identify that as mass. So mass of 2 kilograms. Copper, according to the chart, so you have to flip back to your notes and see that the specific heat capacity of copper is 390 joules per kilogram degrees Celsius. And then we were given 2 temperatures, so it's very important that you figure out which one's the initial temperature and which one's the final temperature. Are you adding heat or are you removing heat? That's important because if you're adding heat, you're going to have a positive delta Q by the time you're done. If you're cooling something off, you should have a negative delta Q, so it'd be losing heat energy. So from the 2 temperatures given, before you even start doing any real math of the equation, you should probably figure out what your change in temperature was. So in this case, it's a quick little subtraction. 80 minus 30 degrees Celsius should give you 50. And we are going to use 2 significant figures, just like this question, a little underline under the zeros there. So that tells me that those zeros are significant. I may not reflect that in my chicken scratch, but I look at the question to tell me that. And as far as the values are concerned for your specific heat capacity, just ignore their order of significance. This is from a chart, so we're just going to assume that it's not a measured number. I know technically it is, but for our purposes, we're going to stick with the measured numbers that are given. So from there, you've got a change in temperature of 50 degrees Celsius. Plug it into the equation. You're given the mass. You know what your substance is, so you have your specific heat capacity. You know what your temperature change is. It'd just be a matter of plugging in all 3 of those terms and then do some multiplication. 2 times 50 times 390. Cancel off the units that you can cancel off. You have a kilogram in the numerator, you got a kilogram in the denominator. You have a degrees Celsius in the numerator, you got a degrees Celsius in the denominator. If you're trying to find the change in quantity of heat energy, then you should have joules in the end. So punch those numbers through. You should get about 39,000 joules in the end. That's one way you can write it down. I personally hate writing all those zeros. I would sooner use a metric prefix. So every group of 3 little zeros like this, you can just exchange that for a kilo. So you can call that 39 kilojoules. But if you're not comfortable with that and you only want to represent it with 2 significant figures like the question should have, then you can just move the decimal place 4 times to the left and call it 3.9 times 10 to the 4 joules. All 3 of those are acceptable. Again, I have my preferred way of writing it, but that's probably what the answer key would reflect, 39 kilojoules, if this was a question that you would have answers for. But both of these are considered correct. So this one's a little bit of a harder question. So in this question, you were given if 3.0 times 10 to the 4 joules of heat energy is transferred to a 1 kilogram block of aluminum that is initially at 10 degrees Celsius, what will be the final temperature of our aluminum. So the number we were given, 3.0 times 10 to the 4, that's 30,000 joules of heat energy. So that's our first thing. Try to figure out all of our givens. So I just quickly highlighted them all. You have 30,000 joules of heat energy. I'll just write it down as 3.0 times 10 to the 4 joules. So that is our delta Q. So if this is all new to you, you have to kind of just get used to looking for the type of unit and associate that with the variable symbol. So joule is corresponding to our delta Q. And I know a few lessons ago when we were talking about energy and chemistry, we were talking about enthalpy, and enthalpy was delta H, and we still use the J for the joule. And that's fine. There's lots of different symbols we use for energy and heat. But the main thing is it's an energy, so all energy is going to be measured in joules. Our mass is 1 kilogram, so it's a nice simple number. Aluminum, so you'd have to go look at your chart. Aluminum should be 900 joules, so 9.0 times 10 to the 2 is what's on your chart. So that's 900 joules per kilogram degrees Celsius. And we know what our initial temperature is. We don't know what the final temperature is. So our initial temperature is 10 degrees Celsius. Since we don't know our final temperature, we also don't know our change in temperature. And if you don't know your change in temperature, you're going to have to manipulate your main equation. So our main equation is delta Q is equal to MC delta T. Some people like to say MCAT as a way of remembering the equation because that delta symbol looks like an A. So MCAT is your way of calculating the quantity of heat energy. So we know Q, we know mass, we know our substance is aluminum, we don't know delta T. So since we don't know delta T, I typically will put a box around it, and I will try to isolate the term that I'm looking for. Since the delta T is in the numerator, I'm going to divide out the two other variables that it's touching, so the mass and the specific capacity. And if I divide it out on the right-hand side, I have to divide it on the left-hand side, canceling off those terms to get delta T all by itself. So I'm going to rewrite it just below here because I usually prefer my equations so the thing I'm solving for is on the left-hand side. It doesn't matter in the end. It's just the way I like to do things. So my equation for calculating the change in temperature should be your change in the quantity of heat energy divided by the mass and divided by the specific heat capacity. So once you got that solved for, you can just plug in your numbers. So your 30,000 joules divided by your 1 kilogram and your divided by your 900 joules per kilogram degrees Celsius. You can cancel a joule there, you can cancel a joule there. Your kilograms will cancel, so your mass will cancel here with this denominator there. And the only thing that's left is this per degree Celsius that's inside a denominator. So down below here, we have a denominator that is in a denominator. And when that happens, due to fraction math, it becomes a numerator. So you can just take this per degree Celsius and you can write it up top. So that's the only time you could have done that with the kilogram as well, but it canceled over here, so I didn't have to bother with that. So this is the only one that doesn't cancel, and because it's in a denominator, that's in a denominator, that's a nested denominator, you get to just bring it out top. Do a little bit of math, you'll see it'll get 33.3 approximately. So I should only have two significant figures. So according to this, 2 sig figs, my mass is 2 sig figs, but I'm not done yet, so I'll just keep that extra one for now, typically for rounding purposes. So 33.3 degrees Celsius would be the overall change in the temperature. So that's not exactly what we're looking for. We're looking for the final temperature. We just know how much it changed by. So because this heat energy was added, it would have gone up to 33 would have gone up by 33.3. So I'll erase everything and just kind of write that last step down. If I'm looking for my final temperature, I know how much it changed by. I know that my delta T equation should be my final temperature minus my initial temperature. So I'm looking for my final temperature. I'll therefore bring my initial temperature over to my other side. And since it's a subtract by my initial temperature, I'll just add it to the other side, which basically means I have my final temperature all by itself. So my final temperature ends up being my change in temperature plus whatever my initial temperature was. So that's just a quick little addition after the fact. So your 33.3, which was our delta T, added to the 10 from the original question, since the aluminum was initially at 10 degrees Celsius. Just add those two together, and by the time you're all done adding 30,000 joules of heat energy together, you should have 43 degrees Celsius as the final temperature of this block of aluminum. So without further context, probably wonder, well, why are we doing this? Well, at the moment, we're just doing math for the sake of math and just trying to get familiar with the equations and how this all works mechanically. We'll get to the why this stuff is a bit more important when you talk about, well, we won't get into this, but when you get into further on in your education, if you talk about material strengths or why certain things are built with certain materials or other materials, it typically will come down to an object's specific heat capacity, its ability to hold on to heat. Sometimes you want something with a high specific heat capacity. Sometimes you want something with a low specific heat capacity for transferring heat energy from one object to another. So I hope that was helpful. If you can, try to do questions 1 to 7 from the practice problems that are available online. We haven't got to mixtures yet. That'll be my next lesson with you guys. Just for now, try questions 1 to 7, and that should be good. All right.